Application of integral calculus, hydrodynamic force on a bridge pillar. Let's explore how integral calculus helps engineers calculate the force of water acting on a submerged bridge pillar. Real-world example, bridge pillar in a flowing river. Imagine a rectangular bridge pillar submerged in a river where water flows faster as you go deeper. Let us consider height of the pillar submerged in water 10 meters. Width of the pillar facing the flow 2 meters. The water velocity increases linearly with depth from 0 meters per second at the surface to 5 meters per second at the bottom. To calculate the total force, we break the pillar into slices and compute the force on each one. Calculating force on a thin slice. Consider the thin slice of water at depth y, with height dy, and width 2 meters. The water speed at that depth is 0.5 y. Using the formula, the small force on the slice is dF is equal to 500 y squared dy. Total force on the pillar. Now, imagine summing up the force from every tiny slice, starting from the top of the pillar and going all the way down to the bottom. But since the force on each slice is different and changes continuously with depth, adding them directly isn't easy. This is where integral calculus comes in. It allows us to smoothly sum all these infinitely small forces into one complete expression. By integrating the thin force across the entire depth, we get the total force acting on the pillar. This integral gives the total force on the pillar from the water pressure acting over the deck. Engineer decision. This calculated force helps engineers design safe, durable, and efficient structures such as bridges, dams, and underwater tunnels, capable of withstanding real-world loads like hydrostatic pressure, wind forces, and vibrations, ensuring long-term structural stability and public safety. Conclusion. Integration is a vital mathematical tool for calculating total quantities when values change continuously. In this case, it allowed us to compute the total force acting on a bridge pillar by summing up infinitesimally small forces across the deck. This clearly demonstrates how integral calculus bridges mathematics with real-world engineering applications, ensuring both accuracy and safety in design.